Welcome back, everyone. In this video, we're going to look at ebook chapter 2, lesson 3, and we're going to be talking about matter waves. Or in other words, the fact that matter, similar to light, behaves both as a particle and as a wave. We're going to use this to address the question of where are the electrons, about where the electrons are in an atom. So let's start with the end in mind. Orbitals, as depicted here on the screen, they describe the probability of finding an electron in a specific area around the nucleus. And once we understand where the electrons are, we can understand information about their energy and therefore about their reactivity. And in the end, that's what we care about. We want to know, why do elements react? How will they react? Can we use that to our advantage? So let's remind ourselves that thanks to quantum physics, quantum mechanics, we saw that light behaves both as a wave and as a particle. And so it has this dual characteristic about itself. And that we saw that it behaves as a wave when we try and diffract it. We saw that it behaves as a particle when we bounce it off of things through the photoelectric effect, or by seeing how it has quantized levels of energy. It turns out that not only does light behave as both a particle and a wave, but so does matter. Electrons, protons, and neutrons, and even atoms, they behave, we can see them behaving as waves. There's a technique called electron diffraction. So similar to diffraction with light, where you send the particle, the light, through a narrow slit and it diffracts. It bends off at different angles with constructive and destructive interference. We also can see that same effect with electrons. And this provides us evidence that electrons, which are a particle, behave as a wave as well. Louis de Broglie talked about this, and he described how all matter would have a wavelength because all matter has wave-like characteristics, and that you can relate that wavelength to the mass and the velocity of that object. But for macroscale objects, for human beings, for baseballs, etc., the wavelength that they would have is very, very small. So Planck's constant is 6.63 10 to the minus 34 joule seconds. If you have a mass of, let's just say, 50 kilograms and a velocity of 1 meter per second, that's going to be a wavelength that is on the order of 10 to the minus 35 meters. That's minuscule. You can't even, there's no way you could get something that small. And so the wavelength of a human being is essentially meaningless. But when you look at the wavelength of an electron, it's much, much closer to the actual size of the particle. And therefore it behaves profoundly as both a particle and as a wave. So if an electron is a wave, then where are they? We talked about earlier how the Bohr model described we have our nucleus and then these electrons that are orbiting around the nucleus. Well, but if an electron is a wave, then it's not at a particular location. It's spread throughout. And so we have to think of a different way of talking about electrons and their locations. It turns out, so Schrödinger, who was a scientist in the early 1900s, he described the path that matter waves can take as being described as what he called a wave function. So just as with a mathematical function, you might have, if you take something and you say if y is equal to x squared, that's going to give this function. Okay, he described the way that that matter behaves as a wave function. He was able to determine mathematically what those wave functions would be that describe the locations of the wave. This is actually a simplified version of the mathematics that he did, and this side of the equation right here is this H. This H stands for Hamiltonian. And you don't need to know much about this equation other than the fact that it uses the wave function and a mathematical operation similar to y equals x squared, that kind of an idea, to relate the wave function and the energy. So we can describe the energy of an electron through its wave function. But that in and of itself the wave function itself doesn't have any physical meaning. However, it was proposed that if you take the wave function itself and you square it, that describes the probability of finding an electron in a specific region of space. Or in other words, as we talked about earlier, the orbitals. So if you take the wave function and you square it, then that gets you the orbital. These provide information about the location and the energy of our electrons. And an orbital describes the allowed energy states for an electron within an atom. It talks both about the energy of the electron and the probability of finding it in a specific region of space. Or in other words, an orbital has a shape. Going back to what we described here, we see these shapes. We can see that they are spherical in nature in some cases, or in these cases they kind of look like we've got two hemispheres or a dumbbell shaped. We might have a four-leaf clover. So these are our SP and D type orbitals. And we'll get more in depth on those. But the basics of what we need to understand from this video is that electrons behave as a wave. We can describe them with a wave function that describes mathematically where they could be in space surrounding an element. And with that, we will pause until we get to the next section. Thanks for watching and have a great day.